Okay, so our first topic in calculus is differentiation, which we said before was to do with rates of changes. Rates of change, I should say. And rates of change are important in many areas of chemistry, particularly in chemical kinetics, quantum mechanics, and thermodynamics. So, in mathematics, when we talk about rate of change, what we're talking about is a quantity of a function called the gradient. A quantity that describes a function called the gradient. So, what do we mean by a gradient? Well, it's best discussed through an example. So, if we draw a set of axes, label them y versus x. Let's draw a function, the simplest function we can think of, so a straight line. A straight line, we know, is characterized by the equation some function f of x is equal to mx plus c, where m and c are constants. Now, the c refers to the intercept of the y-axis of the function, so where the function crosses the y-axis, so here. The gradient is, for a straight line, the same absolutely everywhere, and we can work out the gradients of a straight line by saying extend a line downwards, and then perpendicular to that line, extend a line towards the function. We call the height of this triangle delta y and the base delta x. The gradient of this function is given by m equals delta y by delta x, and that's equal to the gradient. Now, the important point that we need to remember here is that for a straight line, the gradient is the same everywhere. So the gradient is the same all along the line. Sorry, bad handwriting, that says line there. So what we mean by that is if we were to pick any x along this line, along the x-axis, so we'll call this one x0, then the gradient here would be the same as, if we look at another point x1, the gradient here. And we can see that because the gradient is actually a more colloquial word we would use for gradient would be steepness. So the steepness we can sort of see is the same here as it is here. So we'll say same gradient. Now, it's important to be able to generalize this to any function we like, because it's all well and good to talk about straight lines, but many functions that are useful in chemistry are far more complex than a straight line. So it's not too difficult to actually, it's surprisingly easy to, if you will, to generalize this to a function. So generalization of the gradient. And we're going to use a lot of space here, so we'll say start our function, our y-axis here, and our x-axis here. This y and this x. Now we're going to draw a more general function. It will look kind of like an exponential, but that's only for illustrative purposes because it's easier to draw the easiest I find to draw the diagram like this. So if we were to say this kind of function here, then let's say, because we want to measure, we can immediately see that because remember we said that here that the gradient is a measure of steepness of our function at a certain point. So sorry about that. The gradient is actually a measure of steepness of our function, so we can sort of see if we were to draw a tangent line to our function here, the function's kind of more steep here than it is here, say. Right, so the steepness of the line here, we sort of take the tangent at that point. We'll call these 2 points, we'll call this point here, we'll call this one x0, and we'll call this point here x0 plus delta x. Now we can see here that at the point x0 the height of the function along the y-axis is f of x0, because we're denoting this function, I didn't write it before, but this function is f of x, so we're calling it f of x, so the height here at the point x0 is equal to f of x0. Now the height at x0 plus delta x, should then be f of x0 plus delta x. Now we're just going to do a few more draw a few more labels here, but they'll become apparent why we did this later. The distance between these 2 points, between the point x0 and x0 plus delta x, is x0 plus delta x minus x0, so delta x. And the height here is essentially the amount we have ascended along the y-axis, so an appropriate name for that would be delta y, but it's kind of nice to have it in terms of x, so we can see here that it's the difference between this point and this point, so it is f of x0 plus delta x minus f of x0. Now what we're going to do is we're going to extend a line between these 2 points. It's called a secant line. That's meant to be a straight line, by the way. So this is we'll pick yellow, why not? So this is a secant line, and this we can sort of see here that if we were to move the point x0 plus delta x a little further back, what we would have would be we would have a new secant line. Now this new secant line, we can sort of see the gradient of this secant line is closer to the true gradient that we drew earlier. So the true gradient here, we can see the gradient of this line as we move our point a little further back. We'll call this point xi for a point in between these 2 points. As we move as xi becomes closer and closer, we can see that the secant line we draw, its gradient will be closer and closer to this line. So what we really want to be doing is moving the point x0 plus delta x closer to the point x0. So make x0 plus delta x closer to x0. Now this corresponds to making making delta x equal to 0, because if delta x is equal to 0, then x0 plus delta x will be x0. So we'll draw a little, just to illustrate what we're doing, we're going to say, draw a little arrow here. So we're trying to move this point further and further backwards, and as we move it backwards, the secant line will be moving further and further downwards. Its gradient will then start converging on the gradient of the point that we are interested in, the point x0. Now, I'm going to I'm just going to point out that this means that this line here is, I'll write here, this here is the exact gradient, or the exact tangent, whose gradient is exactly the same here. Now, this point here is then an approximate tangent. And the point, the secant line here, the blue one, is a closer tangent. So what this means is, as we move what we want is the gradient of our secant line. The gradient of our secant line is given by gradient equals delta y divided by delta x. That's simply the gradient of our secant line, because this is a straight line, and we did say before that the gradient of a straight line is equal to anywhere along the line, any perpendicular any distance parallel to the y-axis, and then a distance parallel to the x-axis, and we divide the y distance by the x distance. That will give us the gradient anywhere along a straight line. And as we move this closer and closer and closer to the point, the gradient of that line will be exactly the same as the gradient at that point. So we'll say, we should be using a roughly equal to sign here. So this is roughly equal to that. Now, we did say here that if we make delta x equal to 0, then that will be exactly the same. So the gradient at our point x0 is exactly equal to the limit as delta x tends to 0 of delta y divided by delta x. And that's an equality, that is exactly equal. And we said at the top that delta y is equal to f of x0 plus delta x minus f of x0. So it's equal to the limit as delta x tends to 0 of f of x0 plus delta x minus f of x0, all divided by delta x. And this is our new way of talking about the gradient anywhere on any general function. Now this quantity here, the limit as delta x tends to 0 of f of x0 plus delta x minus f of x0 divided by delta x, we say that is the derivative of f of x. And we say we have, in words we would say that we have differentiated f of x. This will become more clear with some examples, so in the next video I will do some examples.